Hey Florian, very nice to see and meet you again.
Nice to meet you, Fabian.
To kick us off, would you mind giving us a little bit of context to your professional journey and current role so far?
Yes, I'm happy to share a few insights and also some deeper details about my background. And nice to meet you, Fabian, and many thanks for giving me the chance in talking in your GenAI podcast. So I'm very happy about that. So I'm an engineer by heart. I was studying electrical engineering and I was focusing on computer science. And after my study, I was doing my PhD in machine learning applied to optical sensor-based scene understanding. So I was using machine learning algorithms and developed a new set of machine algorithms and applied them to real life examples, such as object detection, vehicle detection, human action recognition, or human activity recognition. So everything that you can extract out of a camera. I was also experimenting with inertial measurements units and some LiDARs, but the primary focus was on visual object recognition. And as you may know, GenAI is everywhere. Deep learning is used everywhere. Almost everybody uses ChatGPT-like or DeepSeek-like systems to be more efficient. But in comparison to those emerging GenAI use cases, I was doing my PhD in traditional machine learning. And traditional machine learning always comes into the game where it's especially interesting is for use cases in that you don't have enough training data. So I was using machine learning techniques like Bayes classifiers and boosting algorithms, decision trees, random forest classifiers, support vector machines. So I guess to the audience who's listening, for most of you, those algorithms won't say anything. Interestingly, I was doing that exactly 10 years ago when deep learning and convolutional neural networks were rising up. But interestingly, I was applying those algorithms to real-time problems. So using your iPhone or your camera or your iPad and trying to detect objects in real time. This is possible as of today with any smartphone. We've also used HPCCs, so high performance compute clusters with hundreds of CPUs and GPUs to learn and extract patterns out of examples. After my PhD, I was joining the automotive industry. So I'm born in Hanover in Germany. And I was relocating to south of Germany to Lindau. Lindau, as you may know, is known to be the Silicon Valley of AD-ADAS development because of the close proximity of Continental and ZF and Denso and a few other companies. So I was starting my professional career in Lindau, working in the automotive industry on visual object detection problems for a few customers. I'm happy to speak about that a bit later.
Oh, fascinating. Thank you so much for the overview. Really interesting journey. And let's start there a little bit broader. For my PhD, I've done mostly qualitative research, but one topic that came up over and over again in these conversations with very senior executives in the automotive industry is the topic of vehicle IT architecture. And probably many that have been to any sort of form of automotive conference in the past, they've always heard this over and over that this is really sort of the enabler of loads of the future in-vehicle experiences and related services. But would you mind giving us a little bit of context and nuance around the status quo of in-vehicle architecture and some of the sort of big trends?
Yes, of course. Today, most of the OEMs are relying on so-called distributed EE architectures. So you have multiple different ECUs located in a vehicle. We are talking of about up to 150 ECUs, and each ECU is then supporting a specific domain. During a couple of last years, we are seeing a trend into so-called domain centralized architecture. So automotive OEMs are starting to consolidate and multiple different domains into bigger ECUs that will lead to cost savings, for example, and and less integration work. And today we are seeing a lot of customers moving into centralized, or a lot of OEMs moving into centralized EE architectures. So you're having, for example, one domain controller that takes care of ADAS workload, so autonomous driving and advanced driver assistance systems workload. Then you may have a second domain controller that takes care of infotainment and HMI, so everything that you see that's visible to you as a driver in your cockpit. Some OEMs are even trying to merge those different or two domains into one hardware. And this is also interesting. Those two domain controllers are then surrounded by up to 4 different zone controllers. So OEMs are now trying to integrate and consolidate those 100 up to 150 ECUs that I was talking about earlier into even bigger devices like zonal controllers. You can imagine that a greenfield OEM like those emerging OEMs and EV startups are jumping to those new centralized EE architectures immediately, can jump into those architectures immediately because they do not rely on legacy hardware and legacy software. So they are able to develop everything from scratch. And some other OEMs, like the well-established OEMs, for those it's not that easy to throw away everything what they've developed from scratch and to throw it away and to move into those new architectures immediately. Fact is that those emerging architectures like zonal architectures are the ones that enable us a GenAI use cases within the vehicle. This is, I would say, today with the distributed architectures not possible. Interestingly is also to talk about software, having in mind that customers are transitioning into those zonal architectures.
Just on a very last point around the enablement of lots of the future functionalities, why specifically are centralized? So you mentioned efficiency and effectiveness.
Mm-hmm.
Why specifically are these centralized architectures? Why would they allow these sort of more complex, compute-heavy operations?
Because you have more flexibility in the workload where it's supposed to run. You have more compute power. You have more powerful MCUs, microcontrollers. You have more powerful SoCs available within your system. You have also more modern software architectures that enables developers to be more flexible in moving the workload, in integrating the software into the vehicle controller. You have also more flexibility because more modern software paradigms are used. For example, containerisation is an emerging technology that many OEMs are jumping on. And you have less legacy, I would say.
And from your experience, could that mean that, to mention some of the companies that have been quite public about it, that companies like Tesla, who have been known for and presented to their stakeholders fairly technically how they develop their IT architecture, that they could have an edge over some of the incumbents as relates to bringing some of these new GenAI technologies, which everyone is very excited about, to market quicker?
So I would say those emerging EV startups like Tesla and Rivian, they were able to develop everything from scratch, starting from a green grass. They were able to design their own hardware and software stack based on their own requirements. I would also say that those customers do not that heavily rely on the classical and traditional tier 1, tier 2 and OEM ecosystem. They started to change this paradigm, how the automotive industry is working and collaborating. They are heavily pushing, for example, to go into open source solutions. Tesla recently published an Ethernet protocol that enables those different controllers within the vehicle to talk with each other. They do strongly rely on open source for their self-developed ECUs, while also relying on tier ones for supplier deliverables. So it's I would say much easier for those EV startups to introduce new functionalities much faster. But I'm also seeing that the traditional OEMs are catching up quickly. Especially in Europe, there are numerous initiatives that got started recently to bring those OEMs even more up to speed.
When we had a brief chat a few weeks ago, you mentioned the 8 levels of vehicle software.
Yes.
Let's start there. What are they and why do they matter?
So if we check out a typical SoC, I'm always trying to speak about those 7 to 8 layers to show the complexity of those devices. So I'm referring to 7 or 8 different software layers. Those layers are partially stacked on top of each other, but they are also partially running in parallel. The very basic layer is described by the hardware abstraction layer, or a board support package, which is typically coming from a semiconductor company. If the SoC or the MCU allows, you are setting a hypervisor on top of this board support package to enable a customer to run multiple different operating systems in parallel. We are seeing a strong push by the Linux distributors, but also a strong push by the safe RTOS suppliers. So in order to integrate your existing legacy vehicle coming from those 150 ECUs to a single ECU, you would require a capability to have multiple operating systems running in parallel. And you're also dealing with a lot of legacy. So you may require also a classic AUTOSAR running in parallel. You may have some bare metal applications. So this software entity called the hypervisor gives you flexibility and also sharing different cores by different operating system. It also gives you isolation and freedom from interference. So we are now talking about the board support package, about a hypervisor, and about, I don't know, up to 6 different operating systems on the same hardware. What I'm also seeing as a trend is that customers are now moving over to containerization. So within each operating system, you may have a container runtime. You may also have an adaptive AUTOSAR running within your operating system. You may have a middleware that spans across those different operating systems and across the different applications to enable different applications to talk with each other. You need a kind of communication between the OSs and the applications itself. The stack must be also deterministic and safe, obviously, because often we are talking about mixed criticality, and I was not referring to that, because you are having safety-related application running side by side with non-safety application. So you may require a kind of a mixed criticality orchestrator that takes care of orchestrating operating systems, orchestrating applications, or orchestrating workload if that's possible, and if it complies with ISO 26262. If you are thinking about those maybe 4 to 5 layers already, we are also seeing, or I'm also seeing, a strong trend into ROS 1 or ROS 2 within the vehicle. ROS is referring to Roboter Operating System, which is prominently used for ADAS ADAS applications, because it gives you a lot of advantages over to some other runtime environments. So on top of those applications or within those containers, you may have a ROS stack running, or any other stack that we see applicable with respect to the different domain that the customer is using, or the OEM is using. Those are the 7 to 8 layers of complexity. And this makes it also extremely difficult to manage a system like this. Imagine you're having on your SoC 6 different operating systems that you as an OEM must update over lifetime, maintain, do cybersecurity fixes, upgrade the operating system, the application, configure the hypervisor. It's extremely complex to manage a system like this.
Is it also reflected, maybe a naive question, but also reflected in the respective organizational structures at the... Okay.
Yes, of course. When having this example in mind that you are integrating those different domains into a single zonal controller, you are typically dealing with many different domains within the OEM. So you may have ADAS folks, you may have chassis colleagues or chassis teams and body teams that must integrate different applications into the zonal computer. So you you also require somehow a new way of working and collaborating with those teams, because those teams were traditionally located in silos, and they had their own ECU that they took care, and now you have to merge those teams. You may also require a completely different set of tools running on in your own data center or within the cloud to enable that collaboration. Open source also enters the automotive industry, or entered the automotive industry already. So we are seeing also a strong push by the typical open source consortia and public working groups who are trying to influence that stack. We are seeing different regulations and governance giving subventions to enable working methodologies like this, and obviously also stacks like this.
Initially, we've spoken about GenAI as, I guess, or customer solution GenAI products. So flipping this on its hat and thinking about GenAI as a tool for in-vehicle IT architecture optimizations and use cases surrounding that. Are there any particular trends that you would emphasize in terms of using GenAI for and around in-vehicle architecture internally?
Yeah, so I would say first of all, you need the absolute, the basis, the fundament. And this fundament is in reducing the complexity of those 7 to 8 different software layers. So you would require a much simpler stack, a much leaner architecture that is more easier to manage, especially over the lifetime in automotive. And we are talking about 15 years, as you know. So today we have to reduce the complexity and make this stack more modular and more flexible to enable developers to develop GenAI applications. So to answer your question, obviously, besides of the classical ChatGPT use cases for the driver that I'm seeing coming up at OEM level, I am seeing a lot of potential in using GenAI to design and optimize your vehicle architecture. So it allows us to develop new architectures much faster. Today we are talking about 400 or 500,000 requirements to describe a vehicle. And bringing all those requirements together and letting those requirements, including the GenAI ones, letting those requirements influence your vehicle architecture is key. You have multiple different teams working on your vehicle architecture, wiring harness teams, system teams, whatever. So I'm seeing a lot of potential in doing those design optimizations using GenAI to generate and optimize your vehicle architecture design based on performance, aesthetics, cost constraints, cost reductions, to create different iterations much faster, and also to allow engineers to somehow explore a wider range of design possibilities. I can't tell you, to be honest, how much time is required to develop a complete new vehicle architecture. But I guess today it takes years. Obviously, it depends on the number of people who are working there and how much legacy you can bring over. And this is especially interesting to set up which applications will run on which zonal controller. Which applications, as of today, or domains can we easily up integrate into a zonal controller? What is the effect on the wiring harness? What is the effect on my software architecture? What is my effect on the specific connector that I may require? This is, I guess, a super interesting use case for GenAI during developing vehicle architectures. And I would like to give you an example, which is not specifically focused on using GenAI to design to optimize the vehicle architecture, but it's the first step. It's called KI for BordNet, or AI for BordNet. And for me, this goes exactly into the right direction. This is a funded project by the German government, BMBF, if I clearly remember, where at least one car OEM is part of, and some product companies as well as engineering services companies, and they are exploring this use case on how can we use AI to optimize the botnet itself. I guess there are also use cases to apply GenAI to generate and test different vehicle shapes and structures to improve aerodynamics or structural integrity. This could also be an interesting use case. And what I was super surprised of, it's not new, but if you are developing an aviator system today, you are sending out a fleet of vehicles to collect sensor data. You need examples, training data, from whom you are then extracting interesting information, patterns, to develop your neural net or your algorithm that finally detects a traffic sign. This is always, as of today, the main principle that Cruise and all the other Teslas and AD companies are following. Record data, pre-process the data, extract interesting information, train your algorithm. So where does GenAI is interesting now is to, rather than learning from examples, to learn from human behavior. You can reduce a lot of costs in that area. But I have to tell you a disclaimer, so I'm not an expert in that area, but due to the fact that I was 10 years ago exactly within that challenge, getting training data, getting high quality training data is the most important challenge. Learning from human behavior is interesting. And there are some universities experimenting with GenAI applied to learn from human behavior. And there must be also a startup out of UK. I don't get the name. It was AI or Oxbotica out of Oxford, the startup that was showing recently some interesting success stories on applying GenAI to learn from human behavior. It could be super interesting.
Might definitely have to look that up afterwards. Especially the use cases you described around these 7 different levels and the overall optimization of in-vehicle architecture using GenAI. Where do you think this technology is coming from? Will this be, I know a little bit of a sort of speculative question just from your experience of working with these stakeholders for many years. Do you think this will be more driven by the Tier 1s and or hyperscalers working with the OEMs, or do you think this will be more driven by the OEMs themselves, including the associated capability?
I guess it's clearly driven by the OEMs. And I'm seeing those GenAI use cases popping up everywhere across the automotive industry, but more during the development of automotive products or during the development of vehicles. A common problem is, for example, you will have those 500 million requirements to describe a vehicle. How do you consolidate those requirements down to the most important set of requirements? So there are a few startups who are focused on GenAI applied to requirements analysis, and then in a second step to derive test cases automatically from those 500,000 requirements. So I'm seeing a lot of use cases in that area, driven by the OEMs to make processes more efficient, and I guess also to leave this legacy world faster than they were capable of without GenAI.
We've spoken quite a bit about GenAI now, and I know it's sort of a little bit, potentially in some respects, overhyped, but it's definitely on sort of top of mind and on top of the conversation. But are there any other sort of looking ahead emerging technologies as relates to in-vehicle architecture that we need to be aware of?
Yes, so I'm seeing trend. So talking about POSIX SoCs, I'm seeing first of all a trend into safe and open Linux distributions for specific use cases only. So QM and ASIL-B workloads. There are a few companies out there who recently published first successes in certifying an open source Linux distribution. I am also seeing a huge trend in containerisation. Containerisation allows us to abstract the software better from the underlying hardware. I'm seeing ones and also OEMs who are going into that area in the first phase for non-safety critical workload. But I'm sure that the industry will also find a way to go into safety critical workloads on containers. And if I clearly remember, one of the leading RTOS suppliers or RTOS product companies recently published something to support containerization. Containerization is a clear trend. I mean, it allows us cost reductions everywhere during development phase, going through the V model from requirements management to homologation throughout testing. It allows us an easier integration into CI/CD tool chains and into DevOps platforms. It allows us collaboration, and it gives us a much better reusability. The second trend that I'm seeing is around WebAssembly, and WebAssembly is also, for me, a trend. And I am preparing for our webinar, but during a couple of last days, I saw an interesting article. It was called the hidden evolution or revolution of WebAssembly in automotive. And there are some tier ones published some white papers around WebAssembly applied to automotive use cases, because WebAssembly is a way to integrate legacy software. It's also having capabilities around near native performance. It's safe and secure and sandboxed like a container is also as of today. And most importantly, it's language independent. So you can have WebAssembly dealing with C++ code, and also with Rust and Java code. By the way, Rust is also something that's coming up, and that's used more and more for safety critical use cases. So going back to WebAssembly, I would like to give you a nice analogy. And it's already 10 years ago where a developer or an open source guy ported an ego shooter to the Apple Watch. And interestingly, he used WebAssembly to do this portation. And more interestingly, he was able to not change a single line of code from this 20 years old source code of this ego shooter. And it enabled him to port WebAssembly to the Apple Watch. WebAssembly enabled him to port this ego shooter to the Apple Watch. And it enabled the community to port this ego shooter to any state-of-the-art web browser with the latest technology that your laptop or MacBook is having. So WebAssembly is designed by its concept to be fast, safe, and efficient, and to support any language on any platform. So it helps, or it can help automotive customers to be more independent from the underlying hardware. And it could be also a way to integrate legacy source code to newer architectures.
No, thank you. That's a really interesting overview. As a final question from my side, just building on these emergent technologies and trends, maybe particularly considering some of the GenAI use case we spoke about, but also beyond, what would be your top 3 recommendations to senior leaders at OEMs and or tier 1s in charge of the in-vehicle IT architecture?
So first of all, I guess it's most important to reduce the software complexity of the existing software stack to make it simpler and easier to manage. My second advice would be to discuss and analyze the open source industry and what is available from open source communities. Like this could be a middleware, this could be a WebAssembly, this could be a containerization piece, this could be a basic software stack. Open source is more and more important in the automotive industry. I saw Mercedes publicly stating that open source is within their DNA of any vehicle. I'm seeing many OEMs and also tier ones actively going into this area of open source. So I'm spending some time in identifying potential solutions or to close some gaps is my second advice. And my third advice would be to join the forces and to focus on collaboration among different OEMs and tier ones in a public working group. When I'm talking about a public working group within automotive, I am referring to the Covesa Alliance, for example. I'm referring to the software-defined vehicle project by the Eclipse Foundation, and I'm referring to the initiative from ARM called SOPHY, because those public working groups are most important. And collaboration is also becoming more and more important. And about almost everything that I was talking today, there are some projects running in those open source communities and public working groups around WebAssembly, around containerisation, around reducing the complexity of our next-gen software stack within the vehicle. I got introduced into a brand new initiative called S-Core, a Safe Open Vehicle Core, where BMW, Mercedes, Bosch ETAS, and a few other key players are part of. And they publicly stated, we are now joining the forces to develop one vehicle core stack, one vehicle core software stack. There are many other initiatives out there, and I guess it's also worth to check out the European funded project under the European Chips Act called HAL. It is standing for Hardware Abstraction Layer for Software-Defined Vehicles. So it's a joint initiative where more than 50 different companies out of the European Union are part of, funded by the European Chips Act. And last but not least, I guess it makes sense within that third advice to check out Federate SDV. This is also it's a non-profit organization or association. To be honest, I don't know. I only know what they are doing. And to share knowledge and facilitate collaboration within this changing SDV paradigm, also connected to the European Chips Act. So those are my three advices.
Thank you so much, Florian. It's been a super insightful conversation. Learned loads from you and really appreciate you making time for this today.
You're welcome.